Hello everybody, today I'll be explaining to you the basic concepts of electrical uh, fundamentals. So first of all, we have to understand what an electric charge and current is. So we know that we've got protons and electrons, and each one has a charge, negative charge and positive charge. As you can see, electron is the charge of with a negative charge, and proton is a positive charge. They both have the same value of coulombs, 1.6 times 10 to the minus 19, sorry. The only difference is the polarity. Is it positive or negative? So we have to remember how to use our prefixes so that we have micro, nano, and kilo, and that's one of the basics, so keep an eye on that. Now we've got some formulas we have to remember. So Q equals IT, that is just the charge, which equals current times time, and then you could rearrange it to whatever you need to find the missing value. So we know that, so what is it? Is like Q is a charge, right? And the unit of the charge is coulombs. Current, the unit is amperes or amp. And for time, it's always going to be seconds. So how do we create an electric field? An electric field is made by separating charge. Okay, so what does that mean? So we have in this picture here of the positive and negative charge, where the positive charge has an arrow going towards the negative. So we so normally where there is no electric field, the positive and negative charges in the material are equal in terms of the value of it, the coulombs. But when they have different uh, values where they are not equal, then the potential difference between the layers of charge is made as an electric field, which exists uh, between them. Okay, so um, work has been done, and potential difference is always calculated in terms of volts, V, and it's always relative to 0 volts, reference to the earth or ground. Now, you could also use the example of a water tank analogy if you want. You could have a look at the picture, pause the video if you want. I'm not going to dive into that. Now, here are some important formulas that you have to remember. You got the from charge to power, which is here, E equals V times Q. And E equals V times Q is the energy input that separates the charge through the potential difference. E is the energy input, V is the volts, and Q is the charge. Okay, you also have, which we already talked about, Q equals IT, and then we have E equals VIT. What we have done here is we have replaced the Q in the first formula, as you can see, with IT by knowing that by knowing that Q equals IT. So we have two different ways to calculate for energy. And then power, obviously, all you have to do is divide it by T, because power is energy divided by time. Then we have to know how we can convert energy to electricity. So converting energy, because we know that energy cannot be created or destroyed. It is just transformed from one form to another. So here we have two examples. We have battery, and battery converts chemical energy into electrical energy. Then we have a generator. It converts mechanical energy into electrical energy. Then we got potential difference. So how we know what a potential difference is? So when you have two terminals of a source, just like a battery, you have the positive terminal and the negative terminal. And remember when we talked about an electric field made by difference between the uh, the coulombs in the protons and the electrons, that's how we get a potential difference as well. And in a battery, you got positive terminal and negative terminal. So the potential difference between these terminals of a sort is called the electromotive force. And we always say it in EMF, and it's measured in volts. Okay, so here is a simple circuit. We got the positive terminal, and from the cell, the symbol of cell, you could see there the energy. So we are saying E, which is the electromotive force, is coming out from the positive terminal and then is creating a current, and then it goes to a load or a sink. Usually it could be a resistor. We're going to talk about resistors soon. So now we have something called the ideal voltage versus the ideal current sources. So for an ideal source, it distributes or delivers the voltage in the circuit or across the terminals actually without changing the current. Okay, ideal current source is the opposite. It delivers current through its terminals without changing voltage. Now we got the opposition to the flow of charge. This is where resistance comes from. Okay, so if we have voltage going through a circuit in a specific direction, then the resistor will be opposite to that direction, slowing the voltage down. Okay, so if you have to be thinking about it, why resistance exists? Because you have electrons flowing through the material. However, there is atoms, and these electrons always have to collide with the atoms, so which always have to be impeding their motion. Okay, and what happens is that electrical energy converts to thermal energy. So remember how we said you can make electrical energy or from transferring other energy sources. And thermal energy is always, in any equation of energy, is always going to be wasted energy. And here we've got the thermal energy being made from the electrical energy, and this is called resistance. It is measured in ohms. Because a resistor converts electrical to thermal energy, we call this a sink. Okay, so what can it be used for? So it could be used for heaters, cookers, light bulbs, and anything that is used to heat up something, like a kettle, for example. Now we have some more equations. I'm going to leave it for you on the screen to write it down. And most of these are just coming from the basic, and it is just substituted. You can pause the video if you want. Now, so we have three things we have to understand: conductors, insulators, and semiconductors. Semiconductors are very cool, by the way. Now, a conductor, as you may have known, it is any material that allows the electric charge to flow freely, almost like there is no resistance, but obviously there would be some. Okay, so usually it's metallic, so like copper is a very good source of it's a very good conductor. You got gold, you got so many different things. Now, the opposite of it is an insulator. It does not allow electric charges to flow at all. Now we've got examples. We got plastic, rubber, glass, porcelain, wood, and air. Yes, even air can stop the electric charge flowing. Now, semiconductor, as you could see from the name, semi, it is between an insulator and a conductor. Okay, and we can control a semiconductor to how we want to be as a conductor or an insulator via something called doping. In later videos, we are going to dive deeper into doping. So we got examples like silicon and germanium, but most of the time you're always going to hear semiconductor being a silicon. Now, here we're going to talk more about resistance. So some important equations you have to remember. Now, a wire is also has resistance. Okay, yes, a wire also has resistance, and even a battery has resistance, something we call internal resistance, which we will get to a bit later. Now, how do we find the resistivity? Okay, so resistivity is how resistant a wire is. How do we find it in a wire? Now here we have an equation. Resistivity equals the resistance equals the resistivity times L. And L is the length of the wire, usually in meters. And then we divide all of that by the area, the meters squared. Okay. Now, from the resistance of a wire, we can find other things, something called conductivity, which is 1 divided by resistivity, or conductance, which we are going to have to use later on, which is G equal 1 divided by R, and R is the resistance. Now on the right you can see a table of different materials with their resistivity and conductivity, and you are free to pause the video to have a look at it. Now, so there is different components, electrical components where their resistance change with temperature. Okay, now in this case we have resistance change with temperature being linear, so it's a straight line. Now obviously nothing is perfect when it comes to physics or engineering. Here we are assuming resistance to be changing linearly with temperature. Usually that is something with Ohm's law. Okay, so now here we have 3 equations that will be useful as well. So you could find a resistance RT1, so which equals the initial resistance multiplied by 1 plus alpha 0 T1. T should always be in it's the temperature, Kelvin. And then alpha, sorry, I didn't explain what alpha is. Alpha is just the temperature coefficient of a resistance. Now, so same with current and voltages. As you saw, the previous equations, these equations could also be used for, so it's similar to voltages. So the key idea is that resistors in series carry the same current. The source voltage is shared across them in proportion to each resistance. And voltage current, so here we have parallel circuit, so voltage current and current split. Okay, here adding the resistors will not give you the total resistance. You have to follow an equation. You see the third equation, on the left in blue, that is what you use to find the total resistance. And let's go to the next. So here are some more equations you have to remember, and you feel free to pause the video if you want. Now, so as I said, remember I talked about internal resistance of batteries, right? So here are the equations you can use to find to account for internal resistance. So the RT, which equals the so here the yellow resistor is the internal resistance of the supply Vs, the battery. Okay, now to find it, it is usually the total resistance of the whole circuit is just the internal resistance of the battery plus the whatever resistor we have in the circuit. Okay, so and then we have something called the terminal velocity. Sorry, I meant terminal voltage. So that's the actual voltage that is supplied by for example, a battery, because we've got the internal resistor. So what we do usually is Vs, which is the open circuit. So when the battery is on its own, we did not put it in a circuit. We take that voltage and then we minus from it the currents that is created in the circuit multiplied by our internal resistance. So what happens if the resistor we have in the circuit has the same resistance as in the internal resistance of the battery? That is something called resistance matching. So what resistance matching does is that what it means is that you get the maximum power transferred in that circuit, and usually the efficiency is 50%. You can find efficiency by the input power, P1, divided by the input, and when I say P1, that is the power made by the resistor in the circuit, and then you could see how we can find the efficiency. We have some graphs to show how they are related. So now let's remember again what an ideal versus practical current source could be. Now, so practical current sources are different, okay, because they are more of a realistic model, okay, because of the internal resistance. Okay, so resistance can spoil a bit of everything in a circuit. The internal, we should never forget about the internal resistance. So now we have talked about all of these from the video, and this is just a wrap up and a summary what we have learned. And thank you so much. Thanks a lot for watching this video. I really hope you have enjoyed it and understood more about the basic electrical fundamentals. Have a very lovely day.